Example 5. A guessing game. This game with 4 input of G1, G2, G3, and G4 push button. And 1, 2, 3, 4, 5. 5 output of LED L1, L2, L3, L4, and ERR. Okay. If no any push button assert, LED L1, L2, L3, L4, okay, we will display like this. Okay, only one LED. Okay, we will turn on. Okay. Yeah, something like ring counter. Okay. And rotate. And when some input assert, for example, when the LED L2 turn on, and then if the user or the player press G2, okay, at the same time, that means it's correct guessing. So in this case, LED will turn off, and maybe the player get a chance to answer some question. Okay. And if the player press G2, but the LED, okay, the turned on LED move to L3. So in this case, okay, the LED ERR turns on. Okay, so based on this condition, the first step, we must know the state of the system. Okay. How many states? Okay, you can observe, okay, from the pattern of the output. Okay. How many pattern of this? Okay, first, no any LED turn on. The second, only L1 turn on, only L2 turn on, only L3 turn on, only output L4 turn on, and ER turn on. So there are 6 patterns of the output, right? 6 different patterns. That means this state machine should have at least 6, right? 6 states. Okay. So then that I write state diagram for this guessing game. State S1. Okay. Only output L1 is active or assert. This one. Okay. Note in this one is more type machine, right? More machine, and to save the space when write down the output, I will write just only active output. Okay. The output L2, L3, L4, and ER not active. Okay, you will not write in this case. And for state S2, only L2 active, and S3 only L3 active, S4 only L4 active, and SOK no any output active. That means all LED will turn off. And S state is ERR, okay, error. Only ERR LD turns on. Okay, so now we have got 1, 2, 3, 4, 5, 6 states. Okay, and you already know the output for each state. Then now how about the next state for each state? Okay, if no any input active, the state will change from S1 to S2, S2 to S3, S3 to S4, and repeat S1 again, when no any input active. So you can write the condition something like G1 prime and G2 prime and G3 prime and G4 prime, right? For the transition expression for each arrow. This one also, this one also. Same condition. So you can define the condition for state change when no any input is active. And now if the machine is at state S1, how to change from S1 to SOK? Of course, when L1 turns on, right? G1 must be active. So you can write G1. But it's not enough, because G1 should be this S1 should go to SOK, when G1 active only. I mean, if the player push 2 or more push button at the same time, it's not okay, right? That mean you must write the condition that only G1 active. That means G2 must be not active, and G3 must be not active, and G4 must be not active. Only this one active. Only G1. So you can write the condition like this. For another state of S2, S3, S4 also. Only G2 active, G1 not active, G3 not active, G4 not active. For state S3, only G3 active, G1, G2, G4 are not active. For S4, only G4 active, right? G1, G2, G3 are not active. So it will change from state S1 or S2 or S3 or S4 to SOK. And if the push button are pressing continuously, it stay at state SOK. That means when G1 or G2 or G3 or G4 active, stay at this one until no any input active. Maybe let's back to state S1. So can write the condition of state transition like this. And this one, G1 prime, G2 prime, G3 prime, and G4 prime. No any inputs active. And how about the state S1 or S2 or S3 or S4? Go to S error. How? For example, if the lamp L1 is turned on, if the player press G2, G3, or G4, it should go to SERR, right? So you can write G2 or G3 or G4. For S2, for S2, G1 or G3 or G4. Something like this. So S3 also, right? G1, G2 or G4 active, then go to SER for S4, G1, G2, or G3, right? And if the player, okay, pressing some input, okay, continuously, so it should stay at this state, namely when G1 active or G2 active or G3 or G4, okay, stay here until no any input active. So when G1 prime, G2 prime, and G3 and G4 prime, okay. So now you can complete state diagram. Okay, if I use this one, okay, to continue the design, okay, what is the next step? Maybe you do state assignment, right? To assign binary code for each state. For this example, there are 1, 2, 3, 4, 5, 6, right? 6 states. That means it needs at least how many bits to represent this 6 states? 1 bit can represent up to 2 states, right? 2 bit can represent up to 4 states. So it's not enough. So it needs at least 3 bits, okay, to represent up to 8 states. Okay, and if you observe, because S1, S2, S3, S4, right? It changed, okay, secondary. So you may assign gray code for this sequence. So for this example, let's use this state assignment, namely if no any input assert, so Q2 is 0, and this one is gray code order 0, 0, 0, 1, 1, 1, 1, 0. 4 states S1, S2, S3, and S4. And if some input assert, okay, maybe go to S OK or SER, okay. For S OK, Q0 is 0. For SER, Q0 is 1. Okay, this is state assignment. After that, you may write output table to show relationship about output and the state. Okay, don't forget that, and this is a more type machine, right? More type machine. Okay, the output, okay, based on only state. Namely, for example, for L1 is 1, only this one, right? When it's at state S1. So if you assign Q2, Q1, Q0 of 0, 0, 0, okay, for represent state S1. That means L1 will turn on when the machine is on state 0, 0, 0, right? So you can write the expression like this: Q2 and Q2 prime and Q1 prime and Q0 prime. Okay, for output equation for L1. How about output equation for L2? Only this one, right? So L2 you turn on when the machine is at state S2. S2 is 0, 0, 1. So you can write equation for L2 and Q2 prime and Q1 prime and Q0. Okay, that means L2 will be 1 when Q2 is 0, Q1 is 0, and Q0 is 1. Okay, for this assignment. And how about L3? L3 turn on when it's on state S3. S3 is 0, 1, 1. So we can write equation for L3 as what? Q2 prime and Q1 and Q0. easy, right? How about equation, output equation for L4? L4 is turned on at state S4. S4 is 0, 1, 0. So L4 equal to Q2 prime and Q1 and Q0 prime. And how about ER? Turn on only this one, right? SERR is 101. So the output ERR, okay, you on turn on when it's at state 101. So you can write the expression. Write this Q2 and Q1 prime and Q0. Okay. That's all for output equation. So, okay, now you use three state variable, right? Q2, Q1, Q0. That means you have got what? Three flip-flop, right? Okay, the easy one is D flip-flop for the design. And now you already know output equation, right? So that means now you can write a circuit diagram for output logic circuit G. Okay, we will give output L1, L2, L3, L4, and ER, right? Okay. So now you left only the design of next logic F. Okay, how to design this one? Okay, if you use state diagram to design, you may write a transition list. Okay, namely, you just consider the arc or arrow. Okay, leaving from each state. For example, state S1. There are 1, 2, and 3, right? Leaving arrow. Okay, from state S1. Namely from S1 to S2 with this input condition. S1 to S okay with this condition. S1 to SER with this input condition. So you just copy, right? Okay, just rewrite S1 to S2 with this input condition or transition expression. S1 to S okay, right? With this input condition. And S1 to SER with this condition. Okay, this is for the transition, okay, from state S1. Okay. Similarly, you next consider state S2. Okay, so you just consider the leaving arrow from this state S2. Okay, there are 1, 2, 3. Okay, from S2 to S3, from S2 to SOK, from S2 to SERR. So you can write this one S2 to S3 with this input condition, S2 to SOK with this input condition, S2 to SER with this condition. Okay, and okay, you continue. Okay, for S3 also. Okay, there are 3 leaving arrow. Okay, from this state. S4 also, right? For SOK, there are 1, 2, right? 2 arrow leaving from state SOK and SER. There are 1 and 2, right? Leaving arc, okay, from state SER. So you just list all these transition, okay, to this table. And after that, you just write down, okay, each corresponding binary code for each state. Okay. For example, by this test assignment, okay, you use 00 for S1. That means you write 000, okay, for S1, for S1, 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 S1 also, okay. And S2 is 001, S2, S2, 001, also 001, right? Okay, right. The binary code, okay, for the state. Okay, now the next step, and you just find transition expression, okay, for each state variable. For example, okay, let's start from Q1. Okay, Q1 star. Q1 star will be 1 when the machine is at state S2 and when clock tick, this input condition become true. So we change to S3 with Q1 star is 1. Okay, or this one, or the machine is at state S3 and when clock tick, this input condition is true. So we change to S4 with Q1 star is 1. So you can write the expression, okay, for Q1 star like this. So Q1 star, okay, will be 1 when the machine is at S2 or 001, right? So it's Q2 001, Q2 prime and Q1 prime and Q0. And this input condition must be true. Okay, you just copy this input condition, G1 prime and G2 prime and G3 prime and G4 prime. Okay, so it's, if this condition come true, okay, we change to S3 with Q1 star is 1. Or what? Or start at S3. S3 is 011, right? Q2 and Q2 prime and Q1 and Q0, okay, 011, okay, and this input condition, G1 prime and G2 prime and G3 prime and G4 prime. Okay, that's all for Q1 star. Okay, so now you get transition expression for Q1 star. After that, you may observe that it can reduce some term or not. So someone may observe that Q1 prime Q1, okay, without complement. So you can combine, okay, you can combine these two terms together. So the result is Q2 prime and Q0 and this input condition. Okay, the variable Q1 will disappear, right? Okay. Different only one bit. So now you get this one, Q1 star. After reduce, combine these two terms. Okay. Similarly for Q0 star, you may observe, okay, logic 1 and find out equation. For example, Q0 star is 1 when it's at state S1 and this input condition become true at clock tick, right? So you can write Q0 star is Q2 prime and Q1 prime and Q0 and this input condition. Okay, G1 prime and G2 prime and G3 prime and G4 prime, or this one, right? Q2 prime and Q1 prime and Q0 prime and this G2 plus G3 plus G4, or this one. Okay, Q2 prime, Q1 prime, Q0, or this condition. Okay, you can find, okay, by consider logic 1 of Q0 star. So you get, for instance, expression like this for Q0 star. And for Q2 star also, okay, you can use this one. But if you observe number of logic 0, okay, compare with logic 1, you see that 1, 2, 3, 4, 5, 6, right? But for logic 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So logic 0, okay, is less than logic 1, okay, or not. So you may write down transition expression for Q2 star by using logic 0. Okay, you can. Okay, how? Okay, for example, this 0, this 0, this 0. Okay, Q2 star will be 0 when it starts at S1 and this input condition become true, right? So for state S1, Q2, Q1, Q0 must be 0. So you can write that Q2 star, okay, will be 0. Okay, now want to be 0, right? So you can write it as Q2 or Q1 or Q0, right? Like max term. Okay. Namely, if you substitute the value of Q2 with 0, Q1 with 0, Q0 with 0. Okay, it will be 0 plus 0 plus 0. So it should be 0, right? But if you go to this state, this input condition must be true also. So what should you do? You should what? And, right? Or which one? If you do and, what happened? And with this input condition, what happened? This is 0, right? This is 0, right? 0 and anything is 0. That means no meaning, right? For this input condition. So you should use or, right? But if you use or and write down this input condition G1 prime, G2 prime, G3 prime, and G4 prime, what happened if you use this one? So if the machine is at state S1, okay, this term is 0, right? Plus, okay, when clock tick, this condition become true. That means this term become 1. Okay, when you add together, the result is 0 as you want. No, it's 1, right? So you must invert this condition before. Okay, so you must invert this one, so then it change to 0. Now it becomes 0 plus 0, so you get 0 as you want. Okay, for Q2 star. Okay, so and how about this one? Okay, how about this 0? Okay. This 0 start at is 2, right? 0, 0, 1. So we can write it at q2 plus q1 plus q0 prime, okay, plus invert of this input condition, invert of this, okay, and this 0, this 0, this 0 also, okay. You can write the expression for q2 star at the same method. After that, you bring this term and together, so you get this one, this term and this term and this term. Okay, after that, and you using switching algebra, okay, to reduce number of term and variables, and the result is this one. Okay, and so if you use, for example, if you use D flip-flop, that means D0 equal to Q0 star, D1 equal to Q1 star, D2 equal to Q2 star, right? Okay, same equation. So now you can design next state logic F. Okay, so you can complete this state machine. Okay, well, something that you should know about this example. For this example, you use 3-bit, right, to represent 6 states of S1 to SER. Okay, 6 states. But for 3-bit, okay, it can represent 8, right? Different binary code 002 111. Okay, but you use only 6. That means there are 2 unused, right? To unused state is what? Is 110 and 111, right? Okay, it's unused state. The problem is, what is the next state of these 2 unused states? What is it? Namely, if I write in this state diagram, okay, there are 2 unused states of 1 1 0, right, and 1 1 1 is unused state. So if the state machine, okay, become this unused state, when clock tick, where or what is the next state of these 2 unused states? You know, if you find equation by consider logic 1, okay, for equation of Q0 star, logic 1 for Q1 star, and use logic 0, okay, to between Q2 star. That means the condition that you select the result, for example, for Q0 star first, okay, you use this condition, okay, to determine that, okay, you make Q0 star become 1. Use this, okay, to make that Q0 star become 1. Okay, so you get the result as you want, okay, by using this state and input condition. The state that you don't select, okay, to implement the equation For example, this one, the result is 0, right? The result is 0, right? So that means that undo state 1, 1, 0, and 1, 1, 1. You don't select, right? To find the equation for Q0 star. That means the obtained equation you give 0, right? And here, okay, the value of Q0 star, because you don't use it, okay, to make the equation. So for Q1 star also, okay, you select this, okay, to make this become 1, okay, and the question that you don't use, the result is 0. How about Q2 star? For Q2 star, the equation you use this, and this, right? Okay, to make Q2 star is 0. The condition that you don't use, okay, you give logic 1 result. That means Q2 star for 110 and state 111. It should be 1, 1, right? That means the next state of undo state of this and this is 1, 0, 0, right? And 1, 0, 0 is what? 1, 0, 0 is state S, oh sorry, is SOK, right? 1, 0, 0. That means if the machine go to 110 or 111, okay, and you stay. When clock tick, it go to SOK, right? SOK is 100, right? Okay. So that means we will use equation, okay, to implement this guessing game. Okay? If the circuit, okay, lost or go to undo state 111 or 110, okay, when clock tick, it will go back to normal state by itself. Okay, so now you can use this equation to implement this guessing game. Okay, well, next example. Actually, it's same problem, but please treat it as a next example. Okay. So I will use same state diagram, okay, to design. The difference is state assignment. I will use different state assignment. So for this example, please observe that for each state, for example, state S1, the output is 1, 0, 0, 0, 0, right? And namely, only L1 turns on. Okay. For S2, only L2 turns on. So output is 0, 1, 0, 0, 0. Okay. For S3, only L3 turn on. 0, 0, 1, 0, 0, okay, and so on. So you can observe that. The pattern of the output for each state, okay, are different. Okay, are different. In this case, you can use the output and output of you can use output of the circuit and the output of each flip-flop, namely output variable and state variable are the same. Okay, the same signal. Namely, for the example, you have got 5 output, right? L1, L2, L3, L4, and ERR, right? So if you use 5 flip-flop, the Q5 flip-flop as state memory, 5 flip-flop, okay? This one, 4 and 5. Okay, you can use output of flip-flop, okay, to be output of the circuit directly. Namely, now the output logic circuit G have nothing, just only wire, okay, to connect directly of output of flip-flop, okay, to the output of the circuit. So in this case, you can name, right? You can name this signal as L1, okay, same name of the output. Or you can name different, maybe Q0, Q1, Q2, Q3, and Q4 also. Okay, but for this example, okay, let's use the same name, right? Because it is the same signal in the same wire. So now I used, okay, L1, L2, L3, L4, and ER, right? To represent state S1, S2, S3, S4, S and ER by using its output. Namely, if L1 is 1, okay, L2, L3, L4, and ER, okay, are 0, right? That means now the machine is on state S1. Okay, so when you write transition list, actually it's the same as the previous example. Start from S1, you change to S2 by this input condition. Okay. The difference is the binary code, okay, to represent this state. Okay, different, okay, just different state assignment. And for S2, you use this one. Okay, now, okay, when you can complete this transition list, okay, by using state assignment, okay, that you use the output, okay, signal, okay, the same as output of flip-flop, namely output variable and output variable and state variable are the same. So this kind of state assignment is called output code state assignment. So from transition list, okay, from this output code state assignment, you get something like this. Like this. So after that, you can find equation for each one. For to determine circuit F, right? And you have got 1, 2, 3, 4, 5, right? And circuit G. For circuit G, indicate is pretty easy, right? Because you use this output of flip-flop, okay, become output of circuit directly. Okay. L1, L2, L3, L4, and ER. right? Okay, so you can get output equation easily. Namely, this L1 equal to this state variable. Okay, so you can complete this one easily. And how about circuit F? Again, okay, you just find out transition expression, and then if you use the flip-flop as state memory, the excitation equation, namely D input D of D flip-flop will be the same as Q star, right? In this case, Q star is same as output variable. So you just consider logic 1, okay, output of L1 star, this one or this one or this one. If you consider this one, it is state S4, right? And this input condition come true, you go to S1. That means to check that it's state S4, S4, L1 will be 0, L2 is 0, L3 is 0, L4 is 1, ERR is 0. So the condition, okay, to check this state is L1 prime and L2 prime and L3 prime and L4 and ERR prime, right? And this input condition to make this L1 star become 1. Okay, for this one also the same. L1 prime and L2 prime and L3 prime and L4 prime and ERR prime and this input condition. And this, okay, about this one, Q1 prime, Q2 prime, Q3 prime, Q4 prime and ERR and this input condition. Okay. So when you add these three cases together, so you get equation something like this. First, second, and third, right? Sum together. Okay. Sorry, this one. This one. Sorry. L1 star, right? This one and this one. Sum together. And for L2 star, L2 star is 1. Just read this case, right? L1 and L2 prime and L3 and L4 and L4 prime and ERR prime and this input condition. This is for L2 star. Okay. For L3, L4 and ERR also the same. Okay. So you will see that if you can find, okay. Well, again, how about the next state, okay, for each unused state? Okay, now you use 5-bit, right, to represent the state. 5-bit can have 32, right? 32 different binary code, but you use only 6. That means there are 26 unused state, right? The problem is, how about the next state of unused state? Okay. For example, the state 1 1 1 1 1, okay, and other unused state. Because okay, you for this example, maybe all of these, okay, you select, right, logic 1, okay, to determine the equation. That means the condition that you don't use, okay, you give 0 0 0 0 0 as the result. That means the next state of unused state for this example, okay, every unused state you have the next state of 0 0 0 0, So 0, 0, 0 is what? It's okay. It's okay. That means every undo state, okay, when called T, okay, the next state of undo state you go to is okay. And the next example, okay, same problem of guessing game, but just different state assignment, different state and assignment from the previous example. For example, this one, the undo state of, for example, undo state that beginning with 1, maybe 1, 0, 0, 0, 0. Sorry, not 0. 1, 1, 0, 0, 1, 0. 1, 0, 0, 1, 1, and so on. Okay, or I may write 1, x, 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 x. Okay, it means the undo state that beginning with 1. Okay, it's similar to when we code of state S1. X, x may be 0 or 1. Okay, so what happens if we define the next state of undo state for some input condition and same as the normal state that have a similar binary code. For example, and the undo state that beginning with 1, 1, x, 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 x. If the input condition is this one, G1 prime, G2 prime, G3 prime, and G4 prime. For S1 is go to S2, right? So if I let the next state of undo state, okay, go to S2 also if this input condition become true. So what happened? So you can write, okay, and you can take this transition rate like this, okay, 1 x x x x, okay. If this input condition become true, we go to S2. So if we write some idea, something like this, okay, this normal state. By this input condition, you go to this state. So the undo state that have got similar binary code, okay. So let it go to the same next state, okay. If another input condition, okay, make this state go to this state. So if this one go to this one, so the undo state that have the similar binary code of this one, okay, you go to the same next state, okay. For S2 also, for S2 is 0, 1, 0, 0, 0, right? So the undo state that beginning with 0, 1, okay, you have got the similar binary code of this S2. So if S2 go to S3 by this input condition, okay, the undo state that have got similar binary code of this, okay, also let it go to this state S3. Okay, so by this method, okay, or it's called don't care, okay, state coding. So if you find our equation, for example, for L2 star, it's only one, this one, right? That means you can find equation very easy, right? It's L1 and this G1 prime, G2 prime, G3 prime, and G4 prime. Okay, the variable of L2, L3, L4, and here we disappear, right? So, okay, you can obtain, okay, the shorter expression for each transition equation. Okay, for another variable also, okay, you can find our equation, okay, like this. Sorry, write this one. Okay, and okay, the next topic, okay, maybe that's all. Okay, the next topic and the detail will be next chapter. Okay, to the design, large or big state machine or system. Actually, it's like when you write programming when you coding. Okay, normally we have something like a main program, right, and some subroutine or function that often used. Okay, for the hardware design of digital circuit also. Okay, you may design by using a main machine and have some sub-machine that obtain some function that often used. For example, counter is often used. The main machine may be go to some step and let this counter start to count. We count 1, 2, 3, and then back to the main machine, okay, to do the something for the next step of the process. It's something like this. Okay. For example, from the previous example, guessing game. For the guessing game, I have got LD, right? L1, L2, L3, right? And then it's turn on, right? And run, right? Run, and let the user press, okay? Push button, okay? At the same timing when LED turn on, and then where we have a chance to answer something, okay? So if the player play, one thing may happen. The user may be familiar with the rate of speed of LED, right? When it's circulate or turn on. So to make it harder to play, maybe the speed may be not smooth. For example, when it's turn on this one, turn on this one, turn on this one, turn on this one, right? Maybe okay, then I back to this one. Sorry, let me back to this example. Okay, for the previous example, it may be something like this, right? Okay, same speed. Player will play this easily. Okay, but if you do something and let this LED turn on and then maybe wait one clock tick and let this one turn on and maybe on at this LED 2 clock tick before change to L3, something like this. Okay, it's quite a random rate of change, so the player will play harder. Okay, so to do this, okay, maybe use more signal, okay, to control or add more condition. And let us say it as enable. If enable is 1, go to next step. But if enable is 0, okay, it repeat, okay, this step. From this one also, enable is 1, enable is 0. Okay, and this one. Okay, enable is 1, enable is 0. Okay. This one also 1, 0. So if I use some circuit to generate, for example, generate the sequence of 0 1 0 0 1 1 0 0 1 1 0 1 1 1, for example. So and the machine will go to this one and then repeat this one 1 2 4, go to this and go to this, right? So it not smooth, okay, movement, okay, to make LED, okay, turn on. So the player uh, is become harder, okay, to play, to guess, okay, the timing of LED. Okay, so you may use this circuit, right? Actually it's called LFS, okay, a linear feedback chip register. The detail we will study for the next chapter. Okay? And this circuit, okay, can generate, okay, random sequence of 1 and 0, but actually it's not real random, it's pseudo random. Okay? Namely, it's actually it have some rule, okay, to generate, but for normal human, okay, cannot guess, okay, it will be 1 or it will be 0. Okay, so okay, make this game, okay, more challenge, okay, for the player. Okay, that's all for today.